Hello, everyone. My name is Omid Saberi. I'm a postdoc at the NTNU University. Also, I'm working as a programmer at the Hydrophilics project at WP5. My main duty in this project is modeling or writing software to model Occur system. Occur is an abbreviation of air cushion underground reservoir. In other words, Occur is a pressurized underground reservoir which is located at the end of hydropower, at the outlet. And this system can control outflow by using an air compressor or air expander. If I want to explain more detail about these things, first of all, we decided to model this system. If I want to explain it with these graphs, with two graphs, short term and long term. If we consider the purple line as the outflow of the hydrograph and the red line as the target outflow of the Occur system, Occur will change the purple line to the red line by, I think this is a miss. Yes. Occur will change the purple line to the red line by filling this gap with water from reservoir, because this is a pressurized reservoir, and also store this upper part of the line into the reservoir and make this purple line to the red line. This is for short term working of the Occur, as you see. The long term of the Occur is, I would say, same procedure, but the main thing in the long term working of the Occur, Occur can supply the water amount, which amount we want for the downstream of the river, regardless of the working of the hydropower. It means, as you can see in this picture, hydropower is turned off. Occur can provide the water, regardless hydropower working or not, without influence on working of the hydropower. Can produce continuously water, same as this line, for the downstream of the river, and control outflow of the hydropower. In order to model this system, actually, instead of modeling just this small system, we have decided to model whole hydropower for general hydropower, not a specific hydropower. We decided to write a program which can use for any type of hydropower with the Occur system. This is the advantage of this software. You can use for, I think, as many as kind of a high head reservoir as we can model it. This is the advantage of this research. Therefore, we use so many different language software for writing this code. In this code, we use 4 type of different languages: Fortran 90, Python, GNU+, and CMD. All these softwares are open source software, all of them, and also free. The important thing, all of them free. No one is, you have to pay money, free download from internet. The first software, Fortran 90, we used the Fortran 90 for writing a calculation algorithm code. And in this code, we use MOC method to calculate a parameter of the hydropower, water head, discharge, oscillation in the surge tanks, and also calculate the Occur parameters, such as the reservoir volume, water level, and other things. And we use 2 references, 2 books as references, applied hydraulic transient and flow transient. You can read these 2 books, they are so useful. And after writing this code, we find out one problem, major problem. This software needs 300 parameters to run, especially in TXT format. And this is so confusing. I think anybody else like me couldn't run this software. Therefore, I decided to write interface, graphical interface to make it so easy and friendly user. I use Python to control. This is a picture of this interface, and I take advantage from this opportunity to write this software and put a lot of feature in this interface. The important ones I'm just mentioned, just important one. The first one is you can model hydropower with Accur or without Accur. This is convert to the type of educational or research software. If you want, you can model Accur. If not, you can design the hydropower. This is a great opportunity to develop this software. And also this software, this is a general software. You can model hydropower up to 2 turbines. And also you can use in this hydropower 2 open surge time, up to 2 open surge time and 2 closed surge time, all together or just one of them. This is a good thing. You can disable or enable each one of these parts. But the other option in this software that makes this software so faster, you can load by using this key. You can load previous data. This is so much data. By pressing this button, previous data you have entered, this is appear in this part, and you don't need to enter anything. And this is so good for reducing error and speed up your calculation. But the important issue in this software that makes it so special, I think, in my idea, these parts, these 2 parts, you can programming this software for Accur and the hydropower. It means you can programming a turbine and Accur up to 60 working plan. The important thing, the important issue for this feature is very useful for unsymmetric or non-symmetric working plan. It makes the result more realistic as a real hydropower, because as you know, the hydropower doesn't use the symmetric every day, one time starting, one time closing. No, this programming make the Accur as get a real result from Accur. And also you can up to 2 weeks in a row, you can model it, and it can run and model Accur with turbine up to 2 weeks modeling, and you can find out what will happen for the outflow and the Accur during this procedure. The other part of this software, for printing result of actually this software, I use GNU Plot. GNU Plot is also open source software, and it is a very useful and flexible software. You can, as you can see, you can print different result in a different color, and 2 or 3 data, or also more in the one graph, and different shapes. The more advantage of this software is because the final result of Accur modeling is so huge. This is numbers, and up to sometimes each file up to 10 gigabytes, and you cannot find any software to model 10 gigabyte data. And this software quickly, very quick, all of them printing all of them. The last part of this software is CMD. CMD acting as a glue in this software. It means by running CMD, run all previous software in order. First, CMD running graphical interface and get the data from the interface. Then CMD run the calculation code from Fortran. And after that, printing the results from Fortran. And at the end, CMD make a folder and put each result to related folder. Or in other words, CMD organize the all results. All of them automatically. You just run this CMD and all of them will perform automatically. I think this software is a good sample to show to other one, to show that we can make or write software by using a free software like a Python, like a Fortran, like a GNU Plot, and performed as well as the commercial software. From the accuracy and from perform, all of them, I think it's better than commercial software. Back to the Occur program. For modeling Occur system and modeling influence of Occur system on the hydropower plant, we choose Prospect hydropower plant. This hydropower plant has two turbines. Each turbine has a 60 cubic meter per second outflow. Also, this hydropower plant has two open surge tanks. First one is located at the headrest tunnel, and the last one is located at the outlet. And as you see, Occur is located at the end of part of the hydropower. The main reason we are using Occur in this system, because after hydropower goes shut down, the water level in downstream drops so fast, and salmon fishes will die. And we want to use Occur to increase this change of water level in downstream, and therefore fish has a time to find their way to the main stream flow, and they survive. And for modeling this system for a hydropower plant, the first thing and the thing we need, we have to know how much water we need to save fishes. This data, this calculation have been done by Professor Alfredson team, and this is their results. This shape, they give us the result as a hydrograph, start from 75 cubic meter per second, and the duration of this hydrograph is 4.5 hours. We use this hydrograph as an original hydrograph. Also, we want to investigate about changing shape of this hydrograph. What's the influence of this changing of shape on the Occur result? Therefore, we have selected two different shapes, curve shape and the break line or step shapes. For all these three shapes, we consider same shapes for the reservoir, cylinder shape. And also, we kept constant the area because we want to compare all results, how influence these shapes. The second and important parameter in this calculation and modeling, working plan. The working plan, either for turbine or Occur, has a huge influences on the result of the Occur. We strongly suggested that use the proper working plan for the turbine. We select symmetric working plan for the hydropower, 20 hours, 5-hour working, 5-hour turn off, and 5-hour working and 5-hour turn off. And also for Occur, we select a standard working plan. It means after the hydropower starts working, Occur automatically starts working and fill up the reservoir, and then goes shut down. And after hydropower shut down, Occur automatically start up and release water to supply and increase the water level disruption. The second working plan also, because it's symmetric, this is the same as before. After modeling this hydropower with the software, Occur modeling software, we get two main results. The first row of these pictures is about working plan of the Occur and hydropower. The line, the green line, you can see, this is a hydropower working plan, and the purple line is the Occur working plan. As you see, immediately after shutting down the hydropower, Occur starts working with the different shapes. In the second row of this presentation, you can see the purple line. This is the important part of our calculation. This is the water level in the Occur system. By measuring these charts, we can see how change water level in the Akur reservoir by different shapes. As you can see, 5 meter in a linear, 5.5 meter in a break line, and also 3.5, I think, I can see it here, with a curve shape. And also this is a volume of the water, how we will change in this calculation. Recently, we found out new working plan. As you remember, I mentioned previous slide that working plan has a huge influences on the results. Recently, we find a new working plan. Now I'm explaining this new working plan. In this method, if the yellow part is a working plan of the hydropower and the red part is a Akur working plan, by shifting and removing Akur working plan on the hydropower working plan, this side, we shift Akur working plan on this. There is one certain time available in this system, in this chart, that this volume equal to this volume. This is our key time that solve our problem. This is a start point time for the Akur for new working plan. By modeling and applying this formula in the software, we have a new result. As you can see in these results, you can see this is a hydropower working plan, green line, and the purple line. Instead of starting Akur in the end of the green line or at the shutdown, we start middle of the working of the hydropower. At a certain time, this time is variety value for each shape or each project. But it's starting at the middle of working. And this is a water level at the reservoir. Now we are comparing this result with the previous result to see how influence. This is a 5 meter in linear, and this is a 2.2 meter in, and 5.5, 2.5, and 1.6. This is a huge difference in the reservoir volume. And that's it. This is our key for solution for Akur system. And also this is the corresponding pressure in the reservoir. As you can see, pressure in the new working plan. In this pressure, in this modeling, we got the pressure little bit less than 1 and little bit more than 1 bar for the reservoir. In summary, to explain and concept of our calculation, what we did and what we want to do in this calculation and this software, I can explain it with this detail and design. This is a simple design of Akur system, not final design, simple design. The number of the units is not calculated yet, but this is an assumption. I'm just want to show you what we did and what we want to do. The thing we are doing here, we wrote the software to model Akur system, Akur reservoir. And then we tried to reduce this reservoir volume because we want to reduce Akur parameter, such as the pressure, such as the water level, and other parameter. And by reducing this parameter, the Akur equipment, which is important part of this system, without these equipment, such as an air vacuum, air compressor, or air receiver tank, Akur does not mean anything. Akur is not meaning anything without this equipment. We make these equipment so simple in technology. It means it should be available in market, simple in implement, and also simple in maintenance. In total, we try to make Akur affordable to use. We want to suggest some equipment that's available and companies can use it in their hydropower plant. That's why we reduce this. We wrote the software, reduce these values to these values. In other words, instead of saving fishes in this hydropower by using this volume of water, we just need to, for example, supply this water and prepare equipment for this volume. This is available and this is so simple. And the next stage, this is an ongoing project, and the next stage of this project is finding a proper equipment for this volume, not this volume. And we reduce the reservoir volume and all equipment more than 60%. And this is huge, I think, reduction in the cost and reduction in everything. And the next stage is simpler than this stage, finding a air compressor or air volume or other for a smaller volume. And this is for next stage of this project, and it will be done, I think, in some months. That's it. Thank you very much.
Okay, thank you very much, Omid. A very interesting presentation and very much in time as well. So we have already now, yeah, quite a long time for questions, comments. Yeah.
Patrik Andreasson here. An interesting presentation. I was thinking, I didn't really understand, or I understood this, that you start your cure earlier, but you mean that it has no effect on power generation or the flow rate out from the power plant?
Yes.
I didn't get that. How did that work?
Which slide you mentioned? If you talk about the concept of occur, this is this one. If you talk about concept of occur does not influence on the hydropower working. This is the concept. We start to model this by this important thing. Occur does not influence on the working of the hydropower. It means turbine is working, is not working, is no important, nothing. Occur has a separate system, has its own pressure and reserve water outflow. Occur, because of that, occur is locating at the end. It's not interfering with turbine.
Sorry, maybe I need to rephrase it. If you start earlier and have a smaller volume, doesn't you? I mean the time for a cure to act and the ramping of the flow rate is not affected. I'm sure you're right, but I don't understand it.
I can explain to you. Let us start with this. See, this is it. You don't looking at this occur at just a specific time. Look at before we have before starting occur, we have a hydropower working, and after that hydropower working or not working. Occur will prepare water inside the reservoir if you want to start, for example, if you want to make the starting of the turbine longer, okay? Occur before, because the working plan of the hydropower is like this. Occur can store water, for example, from the previous day. Store water in the reservoir and make the outflow, for example, change the outflow based on the available water in the reservoir. You know, the keynote in this key part, this is reservoir volume of the occur, which make it main rule. How much water you have inside it and how much change can it apply on the outflow.
Yeah, I think
depending on how much water you can save and how much water insert or get from the outflow. This is a little bit confusing, but so simple. Getting water from water wasted from here. We save water from wasted water from outflow and use it from the other time. This is the key.
Yeah. So basically, if you know you have if you reduce production, you start earlier to fill up your cure.
Exactly, because the working plan of hydropower, we know what will happen. This is not sudden things is happening. We know that, and we programming occur what we do for now for future. Okay. You know, that's the key.
Yeah, thank you.
You're welcome.
Okay, there's also a question from Tina Hedlund. I don't know if you want to take it, orally, or if I should read the chat, Tina.
I can take it orally. Two of the questions were quite the same that was asked recently, but I also want to know. First of all, you don't always plan when to open and close the hydropower. You don't know far in advance, at least. So how will it work in those cases? And you showed some numbers about volume in your calculations, but how big volume will you need compared to the river flow? Is it reasonable to use it, or will the volume be so large that it's not actually reasonable in practice?
I've answered the second question, then I will answer your first question. About the volume, see, this is some sample. The main thing in this presentation, the method. The method we got for Akur. We will reduce the volume from 60%, from 600,000 to something around 150,000. The thing we want to show, okay, Akur can supply water for your demand, but don't necessarily need to store all of them, okay? And we find the method for Akur that can just 30%, just 40% of your amount of water you need, it can store it and finish your demand based on your water volume, but don't necessarily need to restore all of them. And the first question, yes, we don't know something. Sometimes something happen in programming of hydropower. We don't know. And this is about some calculation about how we want to program it. That's why, as if you remember, I said I put some feature in the software to programming in the unsymmetric working plan. This is why we have to find, if you want to really want to modeling Akur for the one hydropower in a real situation, we have to use this data. This data we use, this is just some data about symmetric working plan, that this is so simple, but in real working plan of the turbine, we have to use unsymmetric for a long term. What will happen for Akur and how much volume we need. That's it.
And there was, did you answer both questions there?
Sorry?
I mean, did you get answers on your questions, Tina?
Yeah.
I got answers on both questions, but I'm not sure that I'm not sure that it works, but let's see.
Yeah, this is a numerical modeling and some kind of, we have to model it and then talk about it. You know, we cannot just I'm saying, oh, yes, it's possible or it's not possible. I have to get a real working plan of the hydropower and model it with Akur, and let's see what's problem of Akur during this working plan. Working plan, each working plan to each other working plan has a different huge result. Yeah. And that's why I said we have to choose the proper working plan for the hydropower. This is an important thing in modeling.
Yeah, but I think that this is good that you really get this input from a little bit more the practical side, how the running streams are done, and that I also thought about that you sometimes you probably just stop the turbines and don't know it. You need to know it in advance. That is it's right now.
Yeah, we have to model it. We have to model different situation and find the best volume and best value for Akur that flexible for all situation. You know, we cannot model Akur just for one working plan. 10, 20 working plan and find the best volume for all these situations and then design it.
Right. Okay. Yeah, there's still time for questions or discussion points. comments?
Well, just a detail here. You in the beginning you talked about short time and long time operation of a cure, and
Yes.
I guess long time is when you basically empty the cure to create the minimum flow rate or something like that, or
This part, you mean this part?
yeah, it's to create this a minimum flow rate for as long time as possible. You empty the cure. That's
Yes.
yeah, okay.
Yes, yes, exactly.
Yeah.
The key is, you know, this is a simple mathematics. You should design or flexible these things. You know, for example, this volume is injection from the reservoir, and this one goes to the reservoir. You should kind of design that this positive, some of this positive volume, it should be equal to the minus, if you want to the like this. This is some mathematical, that how much water you get and how much water you give, and make them equal. You know, this is a key of calculation. And for simple shape is so good, but for a curve shape or for some complicated shape or for a long term, definitely software will necessary. And that's why I wrote the software with different programming and this different working plan. This is for long-term working. 1 week, 1 month, it should be modeling not just for 1 hour or 1 day. It should be modeling for long-term to find out what will happen for occur, for reservoir and for hydropower.
Okay, yeah, I could, maybe you could, I talked a little bit about it, Staffan, here in the presentation of Work Package 5, but you have also considered the Stornorrfors in Ume Älv or Ume River. Could you comment a little bit about your, what you thought? I mean, you something about.
about Uma River.
Yeah, the Stornorrfors in Ume River, because I think your conclusion is that the variations are so large, so they occur.
Yes, actually, in Uma we don't have any data for river. I haven't received any data for how much water, especially say for Nidelva. We received this data. Let me show you. We received this hydrograph that show we need this volume of the water for the Uma, but for the Nidelva we need this. But for the Uma we don't have just the hydropower. We didn't know how much water we need and how shape of the outflow. Because of that, we assume something. We assume something based on the outflow, huge value of outflow, and this is a so simple assumption and simple conclusion. If this is no problem, if you have an amount of water, how much water Uma need for become, for example, how much water demand downstream needs for the water? You give us the shape or volume, I will calculate it. I will calculate and optimize this value. But still, I don't know the shape and the amount of water. I don't know. I just assumption. This is just assumption.
Okay. Yeah, we need to discuss this. Yeah, for sure. I could also comment on before. Are there any other things here? But since this is the active way of damping, and I know that Knut Alfredsen has also looked at the passive ways, like putting up a weir in the river, and he actually concluded that it occur system and needle is a better way probably. So this is interesting because of course you can think about not having this more active, that you push the water, that it just goes into, or you have a weir that stops it, for instance. So that is good. And before I let Richard will then take over and have the keynote speaker 2 here, and that is about fish modeling. Then the missing part here that you also, Omid, talked about is this hydraulic modeling, and that is about how the river flows and what kind of speeds we get, and also what kind of how the water level changes. So maybe Richard will talk about that. And in Idalva, this is done by Knut Alfredsson's group. In Umeå, this is done here by Anton Burman. So this is what happens. But is there any more questions to Omid, or are there any more questions? Oh, there is one here on the right. Henrik, can you take your question also, or should I read it? The question is, how are the air pumps in the Accure driven? With energy from the plant, or what?
Yes, this is for next phase of project, because till now we try to write software and reduce this volume to become simple air compressor or air vacuum. The most try we have done during these years I have been here, we try to reduce this volume to find the air compressor or air vacuum available in market. And I think with this volume, we reach, with this method, we reduce the volume more than 60%. It is simple to find. And this is for next phase. I will update and calculate and find and finalize this calculation.
Right. Okay, if there are no other questions, then I think I let